All right, let's take a look at section 16.2, which is going to cover line integrals. So things we're going to hopefully learn will be to define and calculate line integrals of both scalar functions and of vector functions. So let's start by doing a quick review of an integral back from Calc 1. So hopefully this diagram looks at least somewhat familiar. We've got some function of x, and we're going to call that y. Y is equal to f of x. Cool. So then if we're starting off right at the beginning of integration, we'd split that function up into several regions, hopefully of equal width, and say that the integral should be the area underneath the curve, which we could calculate by splitting it up into a bunch of smaller regions that will probably end up being rectangles. We define some distance in between each of those x values. We call that delta x. And then that becomes the width of those rectangles. When we take a limit of that delta x, it's going to ultimately end up becoming dx. And it gives us the familiar result that the area under this curve should be the integral from a to b of f of x dx. So if dx is the limit of that delta x, that means that dx is going to be an infinitesimal change in the x direction. All of that said, because I want to talk about what the dx really means in an integral. Part of it really, tells you that x is the variable that we're going to be integrating over. We've kind of started talking about that with multivariable integration. But it's going to be helpful when we go to talk about line integrals to really understand what that dx means. Because it is that infinitesimal change in the x direction. So if we are at any point x, dx is just telling us which way we're going to need to go. And it's that infinitesimal change, so it doesn't really have a length associated with it. It just tells us the direction we need to keep moving in order to compute this integral. So that when we're moving through our integral, we're only moving in one direction. We're moving along the x-axis in the x direction, and our result ends up being this two-dimensional area. So that's the bit of review. Let's try and apply that to a new idea. We're going to look at these line integrals. We're now, instead of simply integrating along the x direction, so instead of just being able to move along that x-axis, we'd like to be able to move along any curve C in space. So here, if pictured in figure 1, we have this pink line that starts down at P0, and we'll move all the way along this squiggly line and end up in the end at Pn, since if we're splitting it up into n regions, similar to the way we did in the Calc 1 example. Dx isn't necessarily going to work anymore, because we aren't simply moving along the x-axis, we're moving along this curve. And if we use s to represent the arc length of said curve, then we're probably going to end up wanting ds to be the thing that we're going to use as an integrating factor, that integrating piece, or an infinitesimal change along the direction of s. And we can see that after moving across this line, which is a one-dimensional object existing in it's a curved one-dimensional object that's out in 2D space, but we're still just moving along some curved line. When we take the integral, we should end up with another two-dimensional area, albeit a curved one that's now going to exist somewhere in 3 space, but it is just some thin area shown in figure 2. If we sort of expand that curved line and throw some function on top of it, so that f of x, which is that function, ends up being the height above the xy plane. And the area of that curved shape should be the line integral along the curve C. Notice that C in pink denoted next to the integral. Again, we'll move from A to B of some function f of x and y ds. So again, hopefully we'll be able to talk about what that ds is. So if we come back over to the line in figure 1, we could split up our curve into some delta s, some small arc length between some evenly distributed points. We can then take a limit here, just like we would in Calc 1, ultimately turning that into ds. So we have some integrating factor. So that ds can be just some infinitesimal change in the direction of s. So that ds, again, is just telling us which way to go. How do we move through this curve in order to calculate this integral and ultimately get an area? So that's great. We at least have an idea of what ds is, which again is just the infinitesimal change along the curve that we'd like to move. But practically speaking, what does that mean? Because we can't really do any math on that yet because we haven't related it to any of the other variables that we have. So let's start by trying to express ds in terms of something that we can understand. So we'll start with our curve C, and we'll say it's represented by some parameterization, r of t, which is equal to some x function for the x value and some y function for the y value. So here, x and y are going to be functions of t rather than just variables themselves. And let's keep going with what we had earlier, and we'll say that s is the arc length. S of t, because it'll be a function of t. S of t is going to be the arc length. Arc length of C. So notice that there is a slight difference between C, R, and S. C is just the name we're giving to the curve. R is the function, the parametric function that actually describes C. And then S is going to be its arc length, which is, again, that arc length is what's going to be helpful to us because it tells us how we should be moving through space, so we can have that ds that tells us how to move through this curve. So we have that piece for our integration. So if s is going to be the arc length of C, means that s of t should be equal to the integral from some starting point, r of a, to some ending point, r of t. So a and t are both going to be t values, a just our starting t value, and t being our ending value. And really, we're going to ultimately end up expressing this as an integral over r. So let's just call that from a to t rather than from r of a to r of t. But we've seen this arc length equation before. It's just the magnitude of r prime dt, which if we express that in some more helpful terms to us, that magnitude of r prime is going to be dx dt squared, right? The derivative of the x function with respect to t squared plus the derivative of the y function with respect to t, also squared, all of that multiplied by dt. So if that is the arc length, s, the derivative of the arc length should be ds over dt. We've seen this before from the fundamental theorem of calculus. This should just be the square root of dx over dt squared plus dy over dt squared. And again, here x and y are both functions in the parametric function r, which describes our curve c. So this is the derivative of that x function with respect to t squared plus the derivative of the y function with respect to t, and then squared. Solve that thing for ds, and we should get something that we're able to plug in to an integral with respect to t. So we can now relate ds, which again is that infinitesimal change along that curve that moves through space, but now we can express it in terms of the parametric variable t. So I can express ds in terms of dt, making for a practical integration rather than just that nice theoretical one that we had earlier. So let's move that into our first definition, line integrals in the plane. So this is going to be line integrals for some scalar function rather than a vector function just yet. So we'll have to start with the assumption that C is a smooth curve and is parameterized by x for the x component and y for the y component. We'll move from t equals a to t equals b, so we have a start and an end. Some function of x and y is defined along that curve C, and then we'll compute the line integral of f along C, which means that instead of moving just in the x direction or just in the y direction, we're going to move along that curve C, or going in the s direction, as we previously defined. And we get exactly what we had earlier, where the line integral of f of x and y ds is equal to the standard Calc 1 linear integral, again, going from a to b of f of x of t and of y of t, switching over to their parametric expressions, times our replacement for ds, which is that square root of dx squared plus dy squared, all multiplied by dt. And note that we can simplify some of what we've written out by calling our parameterization r of t, and then we can just say that our line integral along s is the integral from a to b of the f of r of t times the magnitude of r prime dt. Cool, so that's a lot of talking and theoretical stuff. Let's actually try and apply some of it. So here we have an example. So we're going to evaluate the line integral of 3 plus xy squared ds along the curve C, which is just the unit circle. X squared plus y squared is equal to 1, pictured here in pink. And we're going to want to go across the entire curve, and it should not matter what parameterization we use for that unit circle, as long as we go around it exactly once. So let's go with the standard parameterization. We'll let x equal cosine of t, and we'll let y equal sine of t. Now let's also move these pieces over to the right. And for our a and b, we want to go around this unit circle once. So let's just start at 0 and end at 2 pi. Let's use the easiest or the most standard parameterization for the unit circle. So that means that our line integral, which needs to go across C, where we had 3 plus xy squared ds. What's this thing going to be equal to? We will want the integral from 0 to 2 pi. Let's go ahead and put that in pink to highlight the fact that it's coming from the parameterization that we're choosing. And the inside will have 3 plus x times y squared, where x we said is going to be cosine of t, and y is going to be sine of t. And note that that was y squared. Now we need to multiply that by ds, where ds, again, should be the derivative of the x piece squared plus the derivative of the y piece squared. That x piece has a derivative of negative sine, and then negative sine squared becomes sine squared. Do the same thing for the y component. Y is sine of t, so its derivative is cosine of t. So dy squared should be cosine squared of t. All of that multiplied by dt. So we ought to be able to simplify that a bit. The square root of sine squared plus cosine squared is going to be just 1, since we can use the Pythagorean identity to change sine squared plus cosine squared into 1, which is nice. We won't have to worry about that square root component. So we'll just have to integrate 3 plus cosine t times sine squared. But we can make a pretty quick u substitution. If u is sine, that's going to make du cosine. So this is just u squared times du, easy peasy. So this thing ought to integrate to 3t plus sine cubed over 3, evaluated from 0 to 2 pi. Now, sine is going to have the same value at 0 and at 2 pi, which means that that right term is just going to amount to 0 when we plug in both numbers and take the difference. So we're not going to have to worry about that sine cubed at all. Instead, we'll just look at 3t, plug in 2 pi, and we'll get 6 pi, and plug in 0, and we'll get 0. So 6 pi minus 0 plus 0 for that other term means that that whole thing shakes out to just 6 pi. If we extend that line integral into 3 space instead of just 2 space, so now we have a smooth curve parameterized by x, y, and z, it ends up being very much the same equation that we had before, just with a z component tossed in. So we wanted to keep going with that square root example. Instead of just the square root of dx squared plus dy squared, it'll be the square root of dx squared plus dy squared plus dz squared. But again, it's a little bit cleaner to just write that in terms of the parameterization r. And then the equation doesn't change at all. Just that our function now has 3 inputs instead of just 2. And note that if we just replace that function f with 1, we can get the arc length of c by just integrating, doing the line integral of over c of 1 times ds. All right, let's extend that idea into vector fields. So if we assume that f is a continuous vector field defined on a smooth curve c, parameterized by r, then the line integral of f along c is where, if it's the line integral, it's the integral of f dot dr, where again, r is that parameterization. But practically speaking, that'll look like the integral from a to b of f of r times r prime of t dt. And then that way we can have our integral in terms of dt. So let's take a look at an example in a vector field. So we'll evaluate the line integral of a vector field where it's it's 5x minus y for the I component and 2xy for the j component, or the x component, y component, dot dr, where c is the arc of the circle x squared plus y squared equals 4, and we're going to go counterclockwise from the point 2, 0 to the point 0, negative 2. So again, c is the curve that we're going to move on, but we're always going to need, or we'll frequently need, some parameterization for c, which is where r comes in. So r, I'm going to want to be the parameterization of this beautiful 3/4 circle over here to the right. So r, which is some parameterization, meaning it's a vector. And we might as well use the same, or not exactly the same, but a very similar parameterization that we used in the previous example. This isn't quite the unit circle, since this one has a radius of 2. That just means we'll use 2 cosine t for the x component, and we'll use 2 sine t for the y component. Okay, and we wanted to go from the point 2, 0 counterclockwise to the point 0, 2, which is just the part of that circle that's highlighted in pink. So we're going to go across 3/4 of that circle, which means we'll start at an angle of 0 and end at an angle of 3 pi over 2. Since just want to go to that 3/4 mark. And if we check back up to what the definition we had was, that line integral should come out to the integral of f of r, which means that we're going to plug in the x component and the y component to our function. So let's start by putting the vector in. This will be 5 times 2 cosine. So let's just call that 10 cosine t minus y, which will be 2 sine t, and then do the same thing into that next piece. 2xy will be 2 times 2 cosine times 2 sine. What color do we get if we put blue and green together? Let's just do purple. Everything comes out purple. I don't even think that's remotely true, but whatever. 2 times 2 times 2 will be 8. And then again, we'll have that cosine t from the x part. And we'll have sine t from the y part. And I am running out of space. Right where I put that. So let's just put we're going to write the next part down below, and then we'll combine it here in a minute. We want to take the dot product of that with r prime. So if we get r prime, that should hopefully come out to negative 2 sine t for the derivative of the x component. And 2 cosine t for that y component. And then all of that times dt. All right, so now that we got all that written down, just to slide it down a little bit, move our dot product up. Now it's all written down in one line. And let's go ahead and actually take that dot product. Oh, whoop, almost forgot. Again, we wanted to do 3/4 of this circle because we're starting from the rightmost point and going to the lowermost point. So we'll be integrating from 0 to 3 pi over 2. Since we're not going to complete the whole circle, we only want 3/4 of it. Okay. Now that that's been said, let's move this down here. So the integral from 0 to 3 pi over 2 of what happens when we actually take this dot product. We'll get -20 sine times cosine, sine t cosine t, minus a negative, so plus 4 sine times sine, so sine squared of t, plus into that next piece, 2 times 8 is 16. We'll have cosine squared sine t, cosine squared t times sine t. Oh man, my trig teacher would be rather upset at me for that. Oh hey, my trig teacher's me, kind of. So we end up with this integral here. The first couple parts don't look like they'll be, or the first and the third terms don't look like they'll be too bad. Each of those can be done with pretty easy u substitution. But sine squared is going to be a bit trickier. We're going to want some sort of a double angle formula there. And that double angle formula, if memory serves, let's use the pencil color. We should have sine squared of theta is equal to 1 minus cosine of 2 theta divided by 2. So we're going to end up wanting to use that substitution in for sine squared. So let's move this over to the side. Also move that guy up. And we'll substitute that in. 1 minus cosine 2. Oops. We don't want theta anymore because now we're actually substituting into a problem. 1 minus cosine of 2t over 2. All right, and let's actually compute ourselves an integral here. So if we do all that, what are we going to get? For that first u substitution, it doesn't matter if we pick sine or cosine. So let's go ahead and pick cosine. That way it'll come out positive. If u is cosine, the derivative of u is negative sine. So that'll integrate to cosine squared over 2, meaning that first term is positive 10 cosine squared of t. So noticed that we had a double negative. which got rid of that, and I'm just combining the over 2 with the 20. Plus, into that next piece, we have a constant term and we have a cosine 2t term. That constant term will simplify to be just 2, which means we've got a 2t minus the integral of cosine of 2t should be sine of 2t over 2. Ultimately, that should just be sine of 2t. If we combine the over 2 that was already there, the over 2 that we get from the chain rule, and the 4 all combines to be just 1. So sine of 2t plus into that next piece. This time we're going to need our derivative, or our u, to be cosine, meaning that our du is negative sine. So this should become negative 16 over 3 cosine cubed of t. And we need to evaluate this thing from 0 to 3 pi over 2. Now at 3 pi over 2, sine is negative 1, but cosine is 0, which means that our first and fourth terms will both be 0. And if we plug in 3 pi over 2 into that sine of 2t, that'll ultimately end up being the sine of 3 pi. And the sine of 3 pi is also going to come out to 0. So at 3 pi over 2, all three of our terms come out to 0, with the exception of 2t. 2t times 3 pi over 2 will be just 3 pi. And we'll have to subtract from that whatever happens when we plug in 0. And if we do that, cosine of 0 is 1. So 10 cosine squared of 0 is going to be just 10. 2 times 0 is 0. Sine of 0 is 0. And then we'll have a 16 over 3 cosine cubed. So that'll be just 1 cubed. So that becomes minus a negative 16 over 3. So assuming all of my math is right, which I hope that it is, we should get that line integral comes out to 3 pi minus 10 plus 16 over 3.